viewers to the third segment for the second lecture for the online series of lectures for the course of Dynamical Systems. In this segment of the second lecture, we will discuss continuous dependence of solutions on initial conditions. Continuous dependence of solutions on initial conditions. Okay. So let big U contained in R to the n be an open set, and I be an open interval. Assume f from I cross big U to R to the n is continuous and f of tx satisfies a local Lipschitz condition in the second variable at every point t comma p in I cross big U. Okay, we have earlier seen that for the initial time t0 being in the open subinterval I and p, the vector p belonging to the open set U, the initial value problem, dx over dt equal to ft comma x, and x at t0 is equal to the vector p has a unique solution which is given by a map up from a maximal interval of existence j sub p to the open set U, defined on a maximal interval of existence called j sub p containing t0 okay. Similarly, for another point Q belonging to the same open set U, we get a unique solution U sub Q from J sub Q to big U of the following initial value problem. Dx over dt is equal to f t comma x, and x at t0 is now equal to q. This initial value problem is numbered as 22. The last initial value problem is numbered as 21. Okay, and this solution uq from jq to big Q is defined on a maximal interval of existence J sub q containing t0 okay. We'd like to pose the following question now based on these two solutions. UP, two unique solutions, U sub P and U sub Q of the initial value problems 21 and 22. We would like to ask the following question. Okay, so let me erase everything and write down the question that we want to address now. Okay, question. Suppose that P and Q, these two vectors, are very close to each other. Close to each other. That is, the norm of the difference of these two vectors is very small. Okay, this is how you quantify the proximity. Okay, the norm being very small. The norm between the two, the norm of the difference of the two vectors being very small. How close will be? How close will be UP at T and UQ at T if T lies in this closed interval T0 to T1 for some T1 greater than T0 with T1 belonging to the intersection of these two maximal intervals of existence. Okay. So to answer the question, the idea here is that if U sub P at T0 and Q sub Q at T0, it means that the point P and the point Q, or the vector P and the vector Q, start out being very close to each other, start out being very close to each other, then the remaining values U sub P at T for some time T and uq at t for that time t, for t being in this interval t0 to t1 will remain close to one another if t1 is sufficiently close to t0 sufficiently close to t0. So this is the result, this is the answer actually, and this is what we mean by continuous dependence of solutions on initial conditions. Okay, so if you vary the parameter of solutions uh, you know within a very small interval, the solutions themselves will not deviate much. That's what we say by continuous dependence of solutions on initial conditions. Okay, this is what we mean by continuous dependence of solutions on initial conditions. Okay. So the governing differential equation is actually the same for these two initial value problems, okay, given by the same vector field ft comma x, okay, but the initial values associated with these two initial value problems are different. One is given by the vector p and the other one is given by the vector q, so that the two unique solutions are given by up and uq respectively. All right. So let's have a closer look at this at the answer to the given question. Okay, for this purpose, we let B denote an open ball containing these two initial vectors P and Q, such that the closure of the ball B bar is contained in the open set big U of R to the n that one starts with, and the following inequality holds, which is the local Lipschitz condition. The norm of the difference of the vectors ftx and fty is less than or equal to k times the norm of x minus y for all xy belonging to the closure of the ball, and the mod of t minus t0 has to be less than or equal to delta 0 for some positive constants k and delta 0. So in order to visualize the situation, let me draw a picture for you. Let us first denote by U the underlying open set of R to the n. This is big U, inside which is the ball B, whose closure is given by this solid ball B bar. Okay. Okay. Both the initial points P and Q are contained in this closed ball B bar, and the vectors here for this inequality. So let us denote this inequality. That let us put a number for this equation 22 prime. Okay, and the vectors here in this inequality x and y are also taken to lie inside the closure of the ball B bar x y. Okay. Now we have the real line R, and there is an open interval in this line called the left end point of which is t0 minus delta 0. The right end point is t0 plus delta 0, and t0 being the midpoint. Okay, and we want time to take values in this open interval t0 minus delta 0 to t0 plus delta 0, and x and y, these vectors, will also remain in the closure of this ball B bar. Okay, and these two are positive constants k and delta 0. All right, we assume that T1 is sufficiently close to T0 so that the interval the closed interval T0 to T1 is contained in this open interval that we drew here, T0 minus delta 0 to T0 plus delta 0. Okay. Okay, so let me draw this closed interval here inside this open interval. So T0 is the right end point, and say T1 is here. Sorry, T0 is the left end point. T0 is I have to correct it. Yes, I think I did it incorrectly in my notes. So T0 is the left end point and T1 is the right end point. Okay, good. So T0 is the left end point and T1 is the right end point. Okay, and we want this closed interval T0 comma T1 to be contained inside the open interval T0 minus delta 0 comma T0 plus delta 0. Okay, and that way if we squeeze delta 0, then T0 comma T1, that this interval is going to be very small, and T1 is going to be sufficiently close to T0. Okay, and we also want, okay, and if this is the situation, UPT and UQT, they will both belong to the open ball B for all T inside this sufficiently small closed interval T0 to T1. Okay. This is going to be 22 double prime, equation number. Okay, good. Now we use the integral representations of the two initial value problems, initial value problem number 21 and initial value problem number 22. Okay, what are those two integral representations of the solutions that we have already discussed in the previous segments? UP at T is going to be equal to P plus the integral from t0 to t of the vector field up tau t tau, and this is the case when t lies into the maximal interval of existence called J sub p. This is what we number by 23. Okay, and the next one, the next solution, uqt is equal to q plus the integral from t0 to t of the vector field f tau comma up tau d tau for all t inside this maximal interval of existence J sub q, which we number by 24. Okay, so after subtracting the equation number 24 from 23, we get the following: u sub pt minus u sub qt is equal to p minus q plus the integral from t0 to t of f tau minus up tau minus f tau minus uq tau d tau. This is going to be the case when t belongs to the closed interval t0 to t1. Okay. And let us number this equation by 25. Okay. Good. Now we'll be taking norm on both sides of this equation 25 and then invoke triangle inequality and see that we obtain the following. Okay, let me erase this top part. So taking Euclidean norm on both sides of 25, and invoking triangle inequality, we get the following: up, the norm of difference of upt and uqt is less than or equal to a norm of p minus q plus the integral from t0 to t of the norm of f tau minus up tau minus f tau comma uq tau d tau for all t in t0 to t1. Okay, this is going to be equation number 26. Okay, good. So on the right side of equation 26, tau can take values from t0 to t1. On the right hand side of 26, tau can take values in this interval, right? Good. So, since this is the situation by 22 prime, by 22 double prime, we immediately see that UP tau, both UP tau and UQ tau belong to the ball B. Okay. Now, since the interval t0 to t1 is contained in t0 minus delta 0 to t0 plus delta 0, one has tau, we know that tau belongs to this interval, tau belonging to t0 comma t1, and that is contained inside this open interval t0 minus delta 0 to t0 plus delta 0 by construction. Okay, let me erase this part now, we don't need it. Okay, therefore tau belongs to this open interval, and also the solutions at tau belong to the ball B. Therefore, the Lipschitz condition, hence the Lipschitz condition 22 prime applies, and we can write the difference. So the norm of the difference f of tau comma up tau minus f of tau comma uq tau is less than or equal to k times norm of up tau minus uq tau, which we number by equation 26, so that this is, so if this is the case, so that 26 now reads this equation now reads UPT minus UQT, the norm of the difference of these two vectors, is less than or equal to the norm of P minus Q plus K times T0 to T1, the integral of this, of the norm of these two, the norm of the difference of these two vectors, UP tau minus UQ tau. Okay. So using this inequality here in 26, we get this, okay, which we number by 27, and this is going to hold for all t in this closed interval, right? T0 comma T1. Good. Now let g of t is equal to norm of p minus q plus k times this integral, right, from t0 to t1 of this norm up tau, the norm of up tau minus uq tau, okay, for t belonging to this closed interval t0 to t1. Okay, this is our equation number 28. Okay, I need some space, so let me erase this top part. Okay, it follows from 27 and 28. This is 27, this is 28. It follows from 27 and 28 that the norm of the difference of upt and uqt is less than or equal to g of t for all t in this closed interval, right? This is equation number 29. Applying FTC to this definition of G in 28. By FTC we mean fundamental theorem of calculus. Applying fundamental theorem of calculus to the definition of G in 28. One obtains immediately, one obtains the derivative of this function G is nothing but k times the norm of the difference of these two vectors upt and uqt for all t in the corresponding open interval for t belonging to t0 to t1, this open interval. This is equation number 30. Combining 30 with 29, okay, we get the following. Combining 30 with 29 gives g prime of t is less than or equal to k times g of t for all t in this open interval. Okay, good. So this can be rewritten as, so let us erase this part now. So this can be rewritten as g prime t minus k times g of t is less than or equal to 0 for t belonging to t0 to t1. This is our equation number 31. Good. Well, now, like we did in the second segment, we multiply both sides of this inequality by e to the minus kt first to result in the following: e to the minus kt times g prime t minus kgt times e to the minus kt is less than or equal to 0, and then collect all the terms and use Leibniz rule to write it as e to the minus the derivative of e to the minus kt times g of t is less than or equal to 0 for all t in this open interval, right? This is equation number 32. So integrate both sides of equation 32 from t0 to t, okay, from t0 to t, where t is in this open interval, right? One obtains the following: e to the minus kt times gt minus e to the minus kt0 times g of t0 is less than or equal to 0, which implies that e to the minus kt times g of t is less than or equal to g of t0 times e to the minus kt0. And this is the case when t lies in this open interval t0 to t1. Okay, this is equation number 33. Okay, so now let me erase everything before equation number 32. Okay. Now, remember the definition of G. Let us go back to equation number 28. And let me write it for you if you don't remember. GT was equal to the norm of P minus Q plus K times this integral, right? T0 to T. And the integrand is U, the norm of UP tau minus UQ tau, and then we have d tau. Okay, so this was gt. Okay, so from here we immediately see that if we plug in t0 here in this equation, then we immediately see that g of t0 is the norm of the difference between p and q. Okay. So which we number 34. Okay, so using 33 and 34 together, so plug in the value of gt0 from 34 in 33, which yields g of t is less than or equal to the norm of p minus q times e to the k times t minus t0, right? For all t in this open interval t0 to t1. This is equation number 35. Good. So now recall what we had in equation number 29. So let me erase everything here. Recall equation 29. Let me write it for you here. So 29 was the norm of the difference of UPT and UQD is less than or equal to GT. Okay. So now this is 29, this was 29. Now if I combine 29 and 35, I get the following. The norm of UPT minus UQD is less than or equal to the norm of P minus Q times e to the k t minus t0 for all t in this open interval t0 to t1. Okay, this is equation number 36. Okay, it then follows from 36 that it then follows from 36 that, so you can do it by taking max on both sides, by taking max on both sides. So why we are writing max instead of sup? So try to convince yourself, because the supremum is achieved here in the set. That's why we are writing max. So try to convince yourself why we are writing max instead of sup. So max over all t's, taking values in this interval t0 to t1, the max of all these norms, okay, is going to be less than or equal to, okay, the max happens when t is equal to t1, right? That's the max on the right side, and that is going to be equal to c1 times the norm of p minus q. Okay, this is equation number 37, where c1 is taken to be equal to e to the k times t1 minus t0. Okay, so when you take max on both sides, the max on the left hand side is this one, and max on the right hand side is precisely when you have t to be equal to t1, and that this exponent is this maximum exponent is denoted by c1. Okay, so we have 37. Okay, good. Does one sees from 37, equation number 37, that given, so I think I should write it here. Does one sees from 37 that given a positive epsilon, there exists a positive R such that the norm of the difference of P and Q less than R will imply the distance between these two solutions, UP and UQ, which is defined as this expression, right? The expression on the left hand side of this inequality. Max T taking values in this interval, T0 to T1, and the max of all these norms, UPT minus UQT. Okay, that's actually a metric in the space of solutions. So I'm not going to describe the space of these solutions in detail now, but you can prove that it is indeed a metric using the tools of analysis. So, and this distance between these two solutions can be made smaller than epsilon. Okay. So for every such epsilon, there exists an R such that whenever you make the difference of the two initial vectors P and Q to be less than R, then the distance between the two solutions will also be less than epsilon. So check indeed that using this 37 that for a given epsilon, just choose any epsilon, a positive epsilon. Okay. R equal to epsilon by C1 works in 37. Okay, so you choose an epsilon, and then you see that P minus Q is so you then choose, then R is equal to epsilon over C1 works out, because see that if you plug in R over epsilon here, then you'll be left with just R. Okay. Right. So if you plug in R over C1, sorry, epsilon over C1 here. Sorry, in 37, if you plug in epsilon over C1 here, so you plug in epsilon over C1 here, then C1 will cancel against C1, and all you will be left with is epsilon, so that you will have the distance between these two solutions being less than epsilon. Okay, so this is the existence of such R. Okay, we see that such R exists. Okay, so now what does this result tell us? Okay, let me write it for you here. This result indeed tells us that the solution UP of IVP 21 depend continuously on the initial conditions P for a sufficiently small interval T0 to T1. Okay, good. So this was all about the continuous dependence of solutions on initial conditions. So we end lecture 2 here. In the third lecture we'll go back to the discussion on flow of a C1 vector field, and we'll discuss different aspects of flow maps. All right. Thank you for attending the second lecture.